Greetings, AP Calculus BC students, and welcome to our first lesson that will cover topic 7.5 from the AP Calculus CED. And it's all about Euler's method. Euler's method for approximating solutions to differential equations. Now, to get things started with this lesson, it very likely, if you're watching this, it's been a while since you've maybe talked about differential equations. That was a mainstay back in Calculus AB. Maybe if you're in a course that does AB and BC all in the same year, it's just a few days ago that you talked about solving differential equations. So I'm going to try to remind you about what the idea of a differential equation is first, and then we'll ease into this topic, Euler's method. So what we're looking at is in the situation of Euler's method. It's a numerical approach to approximate a particular solution of a differential equation. So let's say that you know that y prime is some function that might have x's and y's in it, some expression of x and y. And we know that that particular expression does happen to pass through some ordered pair, x0, y0. Well, let's say that we don't quite have the means by which to solve for that differential equation, because if you remember, some differential equations are so complicated that we cannot solve them. So, move myself out of the way here. So what you got to do is you have to think about a way that you can perhaps approximate them. So let's think about this. Let's pretend that this differential equation y prime doesn't have a very easy exact solution curve. In other words, I'm going to color this in yellow so it's really faint to kind of suggest that maybe we can't figure out what it is. And let's say that our job is to approximate some value like right here, some x value. I don't know, maybe that would probably be x sub 2 according to my picture, but it's some other x value. Well, we know that we can draw a tangent line, right? We've talked about how you can find the equation of a tangent line pretty easily with calculus. And maybe we could use that tangent line to approximate the value on the curve. Well, the bad thing is that's not going to be a very good approximation the farther out we take it. It's going to be pretty good in this region, but out farther and farther, not good at all. So what we'll do is we will redirect that tangent line, and we'll talk about how we redirect these tangent lines in a bit. Maybe we have a known value that I'll just refer to as h, which is just a change in x that will allow us to find another point on that first tangent line, and we'll use the slope that we know would be associated with the curve, and we'll draw another line. Now notice I didn't call it a tangent line because I can't really refer to it as such because it doesn't attach itself to the curve anymore. But I think it would probably be parallel maybe to a tangent line. Well, then if I were to use that line to approximate the value that would have been on the curve, it's probably a bit better approximation than the blue line. It's a little bit closer to where the yellow curve would be. Well, if we keep this process going over and over again, it's very likely that we can come up with a pretty good approximation that's going to really reflect what the value on the curve might be at that particular point. So that kind of gives you an idea about what's happening. It's obviously named after Euler, Leonhard Euler, probably one of the most famous, if not maybe the most famous mathematician of all time. He certainly had his hand in so many different things. And if you're a student of higher level math, you want to be very, very familiar with this gentleman because he's very, very renowned in his discoveries of mathematics. So let's take a look at Euler's method at work. So I'm going to scroll this up, find a good place for my camera here, and let's go ahead and go to town with this guy. So our example one says, use Euler's method to approximate the particular solution of the differential equation y prime equals x times y that passes through the initial point 0, 1, and it tells us to use a step size, h being 0.2. Our part A asks us to complete the table, gives us some information about dy and what to do with capital Y, which I'll refer to here in a little bit when the time comes. But obviously, or maybe not so obvious, but what I want to try to convey is the most important part of Euler's method really lies within these first four columns. Now, this is the way that I like to teach Euler's method. I like to teach this in a way that I feel like my students are very comfortable with. My students generally are pretty good at writing the equation of a tangent line. We do it all the time. We know point slope formula. So if we can rely on that idea, we don't have to refer to some formula that I know is oftentimes used to teach Euler's method. It works fine. I've done it both ways. I've taught AP Calculus for almost 30 years. I just find my way to be a little bit better in all the times that I've done this with my students. So what we're going to do is we're going to use the first point 0, 1. And that's what I'm going to put into my X and my Y column. 0 and 1 for the X and the Y. Now, the dy dx, which you all know is just really the slope, right? Or m if you want to call it as such. So that slope can be found by just simply referring back to this formula. And I'm going to go ahead and highlight that formula so that we can refer to it as often as we need to. X times y. So 0 times 1, of course, is 0. Now you have all the makings to write your equation of your line. You can use the point slope formula, which says y minus the y value equals the slope quantity x minus the x value. And then if you want to go ahead and simplify that to get y by itself, it can be very helpful. You end up with y equaling 1. Now, I want to just temporarily bypass the dy and the y column because those aren't going to play a big role in us finding our Euler's method's approximation, but we'll go back to them in a little bit. So what do we do on the next iteration? Well, we're going to then implement our step size. That's how far over from the original x of 0 you're going to now find yourselves. So we're going to let the new x be 0.2. That's 0.2 away. Now that's going to affect what our y is going to be, possibly, because you would take that new x and you would plug it into the x that is in the equation of your tangent line, if there was one, and you would compute a new version for y. Now, because we have a quite unusual result here, y is equal to 1, that means that the y is going to be 1 in the second iteration. Right. Now, that's not always going to be the case. Stay with me and you're going to see a different kind of equation of a tangent line come up in a bit. So now we've got 0.2 times 1 as being our new slope because we go back to this formula. 0.2 times 1, of course, is 0.2. And then here you go again. Point slope formula. Y minus the y value equals our slope, quantity x minus the x value, which happens to be the same as our slope. And if we go ahead and simplify a little bit by multiplying through by the 0.2, 0.2 times 0.2, I believe, is 0.04. And so this, lo and behold, will eventually become y equal 0.2x. And if I add 1 to negative 0.04, I believe I get 0.96, positive 0.96. Now, that might be the last step that we can do without a calculator. All right, and that's perfectly acceptable. You're going to find that you will get to use the calculator at times for these problems. We'll discuss that more later on. Now you go to your next iteration. You're going to use your step size of 0.2. So you add another 0.2 to your x. The y value is not going to be 1 anymore. We can see that because if you plug your 0.4 in for this x, 0.2 times 0.4, that would give us 0.08, right? And if you add 0.08 to 0.96, that result is a 0.176. Hopefully you guys see that okay. 0.176 when those aren't added together. Let's do that again because your teacher here doesn't know how to add. I didn't think that was right. 0.96 and 0.08. How's that? That's better. How about that? 1.04. Maybe I should have used a calculator. I just had my decimal not lined up in the right spot. I was going to say, because our y should be a little bit closer there. So now you're going to multiply 0.4 times 1.04, and this is where you're going to see me go back and forth a lot between this page and a calculator page. So kind of bear with me. So 0.4 times 1.04, this is going to give me 0.4 times 1.04 is going to be 0.416. I'm going to try to move my picture out of the way up here. 0.416. So I've got that as my new slope, 0.416. So that means my new tangent line or pseudo-tangent line would look like this. Y minus the y value would equal our slope times the quantity x minus our x value. Now, to get y by itself, I'm going to go ahead and do that work down here. We essentially would distribute the 0.416, and then I've got 0.416 multiplied by negative 0.4, as you can see here. So we've got our 0.416 times our negative 0.4, and then I'm going to add our 1.04. Right? This guy's going to add over. That way we can do all those calculations at once. So as I said before, 0.416, that's what I had before anyway, that's going to be multiplied by negative 0.4. And then once that's finished up, we can add 1.04, and that's a new value for y, 0.8736. I'm going to go ahead and keep all of the decimal places intact. 0.8736. And I said that's the new value for y. I should have said that's the new y-intercept in the third equation. All right, we only have one more iteration here to go in the table. So we're going to go to 0.6 now. Now that's going to cause us to have a new y. So I'm going to replace this x with 0.6. So I've got 0.416. That will be multiplied by 0.6, and then I'll subtract 0.8736 now. So we go to our calculator, and it's going to say 0.416 multiply by 0.6, and then I will subtract 0.8736, I should say, 8736. And that's going to give me 0.624 with a negative. 0.624 with a negative. So that's going to be this new number here, right? So you know what? I wanna reconsider this. Let's go back. Let's see. On our calculator, 0.416 times x is right. 0.416 times negative 0.4 plus 1.04. What did that give us again? That gave us a positive 0.8736. You know what I did? I put a negative in that. We want a plus right here, you guys. Right? It's kind of tough kind of going back and forth between the two applications. So I'm just making excuses, but let's see if we can fix that. Now, if we put 0.6 in here for x, I should have had a plus sign there. So if I go back to the calculator, this calculation was almost correct. That should be a plus sign. That's what we want there, right? 1.1232, 1.1232. So that is actually going to serve as our next value, 1.1232 as our next value of y. Now these two things are going to get multiplied together, and I probably understand that you can type things in and know how to do this, but I'll go ahead and do it along here with you. And that's 0.67392, 0.67392. So that's our new slope. And then our last equation of the line that at least that we have to write in our table is going to be pretty messy. It's going to look like this. Now, I think at this point, I think you guys are starting to get it. I think you get the repetitive nature the iterative process that is Euler's method. So if we were to get y by itself, we would distribute this 0.67392 into the x, and then if we multiply the 0.67392 times the negative 0.6, and then add over this 1.1232, trust me when I say we get 0.718, and I'm just going to use as many decimal places as I've got here just to kind of emphasize what's happening. Okay, so that would pretty much finish most of the table. Now, I do want to talk a little bit about this dy column because a lot of kids get bugged by that, and sometimes the dy column is kind of a neat thing to look at after the fact. But when it comes down to it, dy by definition can be thought of as dy over dx, which is our slope, times our dx. Well, the relationship that I want all my students to make here is that your dx is just the change in x, or the h increment, how the h grows. So if we have a dx that's 0.2 in this problem, it seems interesting to see, well, what's the dy? Well, it turns out that the dy is nothing more than the dy over dx multiplied by your h. So it's everything that you have in this third column right here multiplied by 0.2. So if I take 0 times 0.2, I of course get 0. 0.2 times 0.2 is 0.04. And if I continue that, I know these are going to get a little bit tougher to do, but a calculator could certainly handle these pretty well. This one's pretty bad. It's 0.134784. Now, the y prime, or the capital Y with the star, that would be the exact value of the solution to the differential equation. So we're not going to be able to do that until we finish the final part of this problem, part C. Now let's kind of scroll up and see what's happening in these other portions. We're asked to approximate y of 0.8. Well, if that's what our task is in this next part, well, that would have just been the very next row. In other words, if we had, say, a fifth row and we had 0.8 carry down because that's the next x because of the rate, the h of being 0.2, then whatever we put right here is that approximation. We got to find this question mark. So really, all we've got to do to approximate y of 0.8 is to take our 0.8 and plug it into this pretty nasty expression, 0.6739 times 0.8, and then we'll add the 0.718848. And then again, I know that you can manipulate this with a calculator. That's not what I'm trying to accomplish here. I just want you to see the general progression and see that if we type all this in, we would end up with 1.25798. Now keep in mind, as long as you would round your final answer to at least 3 places, that would be an acceptable answer. But I'm trying to maintain as much accuracy as I can, hence the gobs and gobs and gobs of decimal places. Okay, we're nearing completion here. When we go to the next page, we see that there is going to be a part C to this question. And that part C says, solve this differential equation, dy dx equal x times y, with the initial condition y of 0 is 1. Now, this is a problem that we could have actually solved, and this is going to be great practice for those of you who've been away from solving differential equations for a while. So what we're going to do with this, if you recall, is we're going to divide the y over to the left and multiply the dx over to the right. That is what we call separating the variables. Maybe this is starting to ring a bell. Then we would integrate both sides. When you integrate 1 over y, you get natural log of absolute value of y. And when you integrate x, you get x squared over 2, and we'll put our constant of integration on that side. Technically, there would be 1 on both sides, but we'll consolidate them and put them on the right. At this stage, you can go ahead and use your ordered pair, 0, 1. I like to find the initial condition first before I solve for y. So we'll plug in 1 for y, and we'll plug in 0 for x. 0 squared over 2 is 0. And we find very soon that c is just 0. It seemed like a waste of time, but it was important. Natural log of 1 happened to be 0. We got lucky. C being 0 is going to be easy to work with. So therefore, that means that really we have the natural log of the absolute value of y is just equivalent to x squared over 2. Now, because y is 1 in this problem, you'll notice that this y value is equivalent to 1. That means that we are certainly going to be dealing with the situation where the absolute values really aren't going to come into play, because there's no way that this y could be 1 and some like negative version of 1 at the same time. It wouldn't be a function. So we're going to get rid of the absolute values. Basically, you just kind of look very intently upon that value. If it's positive, you can move the absolute values out of the question. And then we can then cross the bridge. We can get y by itself by exponentiating. So y would be equal to e to the x squared over 2 power. And at that point, we have our official solution. Now what we're going to do is we're going to take a look at our new part D here. Find the difference between the exact value of y of 0.8 and the approximate answer that we found in part B. Well, if we go back to part B just temporarily, we might recall that we had this y value of 1.25798 that was serving as an approximation for the y of 0.8. So 1.25798 is what we've got there. So we'll write that. Y of 0.8 is approximately 1.257, and I believe that was a 9 and an 8 if I'm not mistaken. 2.579 and an 8. Now, it says to go ahead and find the exact value of y of 0.8. Now, that's going to be a little bit tough to write as a decimal that's actually going to basically not terminate, because by the time that we say that we're going to plug in 0.8 in for our x up here, and then divide by 2, it's very likely that we're going to have to round that decimal. So we'll go to our calculator, and I'm going to doc B all this out to kind of give us a clean slate. And if we type in e raised to the quantity 0.8 squared divide by 2, that gives us this 1.37713. But as you can tell, that decimal doesn't terminate. This decimal actually goes on forever and ever. 1.37713, we're going to call it, but I'm going to probably have to give it some kind of a bit of an approximation because I can't carry it out too far. So we'll stop, say, right here. And it says to find the difference between those two. Well, I'll just subtract these two answers, 1.25798 from that, and that would give us 798. That would give us approximately 0.119. And I'm going to go ahead and stop there at the three decimals, so that if I subtract the exact minus the approximate, if you recall, I get approximately 0.119. And basically what this is trying to do is it's trying to tell you that we're pretty darn close. 0.119 isn't too terribly far off of finding our actual answer when it was something pretty hideous, right? E to the 0.8 squared, all divided by 2. And that was all due in part to this method known as Euler's method. I hope this helps a little bit. You're going to see a few more videos over Euler's method in the next couple of series with this particular topic, and certainly you can enhance your understanding of this wonderful tool by watching them. We're so glad you joined us, and we'll see you next time.